Hi, welcome to a new session in Power Electronics module. Today we are going to cover tutorial, and the tutorial is a set of problems that we are going to solve together. So we have here some problems covering what we cover in the lectures regarding the energy and power calculation, the RMS and average values, and also the efficiency. So we have about 5 questions. Okay, so we'll go through some of them in this video, and the remaining will be covered in the next video. So let's have a start. So here is the first question. It says voltage and current for a device are shown in figures below, which this one is the voltage and that one is the current. So what is the requirement now? We have to determine the instantaneous power absorbed by this device. So if we have the voltage and current going across the device and going through the device, actually it's very easy to calculate the power by just multiplying them. But we don't have here numbers. We have waveforms. So the easy way is to multiply each portion of this waveform with the corresponding waveform of the current waveform, and that will give us the instantaneous power. So now the solution will be, we have to draw here x-axis and y-axis, but this time the y-axis is the instantaneous power of t, not the average power. Average power is calculated by the integration of the instantaneous power. Okay, now after multiplying, I think you agree with me that the multiplication is divided, because we have here, for example, this one here, we have some values, and we have here another value different. We have here another value, and here another value. Okay, I mean by another value, we have two values to be multiplied together. They are different during these transitions. Okay, so the first transition, it says we have here about a 20 volt, and we have here 20 volt. Okay, because this waveform is a 20 volt, and that is 20 ampere. Okay, so it will be the multiplication will be about 400 watt. Okay, and then the voltage is 20 volt, but the current down to minus 15 volt. Okay, so it will jump to minus 300 watt. Okay, and then this is at 6 milliseconds. At 10 milliseconds, the voltage now becomes 0, and if we multiply it by any value, it will go to 0. Okay, and then it will continue 0 until the 20 millisecond, which is the period in this question. Again, it will go to 400 and minus 300, and then 0 again. Okay, so the duration in this question here, I think you will agree with me that the duration, which is t, equal 20 millisecond, which is this point, right? And this point is 10 millisecond, and this point is 6 millisecond, right? Okay, that's the instantaneous power. Now what is B? So we finished the first one. What is B? Determine the energy absorbed by the device in one period. The energy, we know that the energy equals the integration over the period, because the question says here in one period. Okay, so over period for the instantaneous power that we got. And I think you will agree with me the instantaneous power is also has some portions. Okay, the first portion is from 0 to 6 millisecond. The second portion is from 6 millisecond to 10 millisecond, and the third portion is 10 millisecond to 20 millisecond, which is 0, so we don't need to consider it. So let's consider the two portions, which are from 0 to 6 millisecond, and the value for the power is 400 watt dt, plus we have from 6 millisecond to 10 millisecond, okay, and the value for that is minus 300. And there is another third portion which is 0, and there is no energy in that portion, so that's why we ignore it. Okay, so let's say now we have to make this integration, and I think you will agree with me that this is constant, the 400, so it can be out. I will just make the first one in detail. So dt, this one is nothing there, and here minus 300, 6 milli to 10 milli dt. Okay, and now you know the integration for 1, okay, it's t, and that t will be from 0 to 6 milli minus 300 t from 6 milli to 10 milli. All right, so now let's continue. This is 400 times t, it will be 6 milli minus 0, it will be 6 milli here, minus 300 times t, and t is 10 millisecond minus 6 millisecond, it will be 4 millisecond. Okay, so you can just do this job, and that equals 2.4 minus 1.2, and this will give us 1.2, and that is energy. Unit is joule. And the third one is determine the average power absorbed by the device, the average power. And I think you will agree with me that the average power, which is capital P, we can write AVG equals 1 over T, the integration over 1 period, the instantaneous power. And I think that portion is already done, okay, before, and that's the energy. We done it here exactly because we integrated the energy over 1 period, so it's the same used in the average power equation, so we can just use it as it is. Okay, so now it will be 1 over T, and that is the energy we calculated in part B. Okay, so that means it will be the energy, which is 1.2 joule, divided by the period, which is here 20 millisecond. All right, so divided by 20 millisecond, which is this, that will equal 60, and the power is in watt. So that's it for this question. We calculated the instantaneous and then energy and average power, and it's now done. And now here's the second problem. So we have here the current in a 5 millihenry inductor, as shown here in figure A. We have 5 millihenry inductor, and that is receiving a current which is the waveform I of t, shown in figure B. Okay, so is the periodic triangular waveform shown in figure B. Determine the voltage, instantaneous power, and the average power. So we have to determine the voltage across the inductor, the instantaneous power, and also the average power. First, I think we, just to make it easy for us, here's the voltage and also the instantaneous power axis. Okay, and I think you agree with me that the voltage across the inductor equals L di by dt. Okay, so there is no doubt about this one, and we have I of t as waveform. The di by dt, this is the term that describes the slope, or can be calculated by the slope that can be calculated or obtained from the waveform here. Okay, and that L is 5 millihenry from the question. Okay, and by this I think we can get VL. So now let's look at the waveform itself. We have I of t, and if we just look at some portions of that, so the first portion is this one. Okay, and that portion here has a slope. What is the slope of this portion? because once we calculate the slope, we got I of t already, okay, the I of t. So the slope of this one is y minus x, the y difference minus x difference. And when we look at the y, we have here 4 amp minus 0 amp, so it will be 4 amp divided by the duration for that exchange, which is 1 millisecond. So here's the slope for this portion. What about the slope for the second portion, this one? It changed from 4 amp to 0, okay? So the change is minus 4 amp divided by the duration of that exchange, which is from 2 millisecond to 1 millisecond, which is also 1 millisecond. So we got the slope for each portion, and we can do the same for the VL. We can divide it by 1 millisecond here and also 2 milliseconds there. And then we say for the first portion we have VL, okay, equals 5 milli times 4 divided by 1 milli, which is this slope. All right. So I got this one, and that will equal 20 volt. I think this is wrong here, should be seconds. Okay, that can be corrected, no problem. Okay, the voltage is 20, so the voltage here is a 20. And the voltage during this period here, from 1 millisecond to 2 millisecond, is minus 20, because we have here the same slope, but the minus equation or the minus sign here. So it will be like this, and then we return to 20 and minus 20 and so on. Okay, so we have here 20 volt and we have here minus 20 volt. Okay, this is the voltage across the inductor, and as we see here, the voltage across the inductor can change instantaneously, but the current, no, it should change gradually. Okay, and to calculate the instantaneous power is the multiplication between the voltage and current. And by looking at the voltage, we have here a constant volt times any value, okay, which is this linear function. It will be the same linear function but scaled by the voltage. Okay, so what I'm expecting here, the instantaneous power will start from 0, because this is 0 current times 20. It will start from 0, and it takes the same exact function like the inductor current, and then the peak value here will be, we have here 4 amp times 20, it will be 80. So I'm expecting here this peak to be 80 watt. And then at this point here we have 4 amp, and that jumped to minus 20 volt. That means we have minus 80 watt. So the 80 watt here jumped to minus 80 watt. Okay, and then we have another portion which is here minus 20 times this line here, which has a slope of minus 4. That means minus 20 multiplied by minus 4 divided by 1 millisecond. So it will be positive. Okay, so the slope now will be positive and go to 0 at that point, and then continues like that. Okay, and then go back and continue like this. So this is the instantaneous power waveform across the inductor. Okay, let's go now to see what's the second one. We got the voltage, we got the instantaneous power, and it needs now to calculate the average power. Okay, which is, we know the instantaneous power equals I of t multiplied by V of t, and the average power we should average over t. Okay, and I think you will agree with me, the period here is 2 milliseconds. Okay, because it starts repeating itself at 2 milliseconds. Okay, or every 2 milliseconds, which is P of t here dt. But I just want to tell you something very fast. If you found that the area in the positive half equals the area in the negative half, okay, that means the average power is 0. And also you can conclude that from the voltage waveform. See this one? So the area here exactly equals the area there, because we have the same duration there and there, but same value with different polarity. That means they will cancel each other, and the average value here for the voltage, for example, the average value for the voltage will equal 0 because sides. Okay, and that will reflect the same for the average power. We have here the same area as this one. You can really calculate that one and have the equation for this one, but I think it's very easy just to say it's 0 across or consumed by this inductor. So what is the conclusion by this one? If we have this current going through an inductor and we found this voltage and this power finally, and the average power is 0, that means the inductor doesn't consume any average power, okay, or real power. So we can say it's lossless component. Okay, if we deal with DC signals and components. So this current now passing through the inductor, but the inductor actually doesn't dissipate any power. And that's good, because sometimes some converters, they rely on this to make lossless converters, but the losses sometimes happen if that inductor has a small series resistance inside it or embedded in the wires, so that resistance will dissipate some power if we know the value of that resistance, because the power dissipated by a resistor is I square RMS times the resistor value. Okay, so I think we finished for this one. Let's now jump to problem number 3. The current through a diode is shown in the figure below, which this one, I of t. Determine the average current, and the arm is diode current, the average and RMS values for this current. If T1 and T2, T3 have these values, the frequency is 250. The Fs is 5 kilohertz. Okay, Fs is I think we will use it just to manage this value here, which is omega s. And I max and I know IA equals 150 ampere. Okay, so we have some values here that they are the peaks for this sine wave part and the maximum for this function here. Okay, I think you will agree with me that the period is already here done as t. Okay, so what is the average current? To get the average current, I think it is this equation always of I of t dt. Okay, but now we have different functions distributed over the period itself. Okay, so we can really say we have this value. Here's t1, okay, plus we have another value for this function, which is this t2 to t3. Okay, so if we got the average value for this one and the average value for this one and combine them together, I think we will get the average value for the whole period. Okay, and that can be done by the same way, by separating the integration itself. So let's now start by saying 1 over t, and I think t, let's now just make it here, equals 1 over the frequency, which is 1 over 250. Okay, let's say now we have the integration now from 0 to t1, and the function from 0 to t1 is already given here as I max sine omega st dt, and there is 0 here, so we will not integrate it, and we have this portion here, which is another integration from t2 to t3, and the function here is just a constant, which is IA. dt. Okay, and that all multiplied by 1 of t here. All right, so now let's just substitute some values. We have 1 over t, 1 over t, because we have the frequency equals 1 over t, so we can get the 1 over t as the value of the frequency, which is 250. Okay, so we have here 250 multiplied by, we have here the integration of sine. So some integrations that you should know from math background or math modules. Okay, so the integration for I maximum is constant, so I can take it out, and the integration for the sine is minus cosine omega st divided by omega s. This is the integration, and the integration will be from 0 to t1 plus the integration for the second side, which is this one. It's constant, so it's very easy. IA is constant, and the integration for just one, it's t from t2 to t3. If you didn't get the integration, you have to revise some math or look at integration table for these. All right, so just we have to substitute these values here in the value of t, which is 250 times I max times minus cosine omega s t1, okay, minus cosine omega s 0, okay, plus IA times t3 minus t2, and that will equal 250 I max. Now and we have here omega s. Okay, so I think you will agree with me that cosine 0 is 1. Okay, no doubt about this. But what about cosine omega s t1 divided by omega s? We can really say, we can take the numbers from up, which is here. T1 is 100 micro, and omega s, by the way, omega s equals 2 by fs. Okay, and we have fs here to be 5 kilohertz. Okay, so we can calculate that. I want you to spend just 1 minute to calculate cosine of omega s, which is this value, times t1, which is 100 micro, divided, after getting the cosine, divided by omega s, and see what is the value here. And I think you will agree with me that if you calculated cosine omega s t1, just this is as alone, cosine omega s t, you will find this value is just 1. Okay, I want you to be careful about the signs because we have here lots of signs. So now let's summarize it. And yes, we have here omega s, don't forget it. So that will end up to 2I max over omega s. You have to make sure that you got this one. All right, so I think we can calculate it later. We don't need to compensate now. And after taking the numbers from the equation above there, or the question, all these numbers, so we have here 250 times 2 times I max equals 450. And after calculating all that, make sure you got the number 12.79 ampere as average value. And now for the RMS value, I think we have agreed before that I of t can be decomposed to 2 signals, which is this one and this one. Okay, so what I mean, we can get the RMS value, RMS value for the whole waveform, by calculating the first RMS value square plus the second RMS value square. Okay, and what I mean by the first and second, this is the first and this is the second. Okay, I think we can get both of them from the slides, because we have some examples covering that one, and we have some examples also covering that one, and we can really just take them from that table. So the first IRMS from the slides, it equals I peak square root of delta over 2. This is from the slides. And looking at what we have here, I peak, which is I maximum, and the on time we have here T divided by the period, which is T. This is the delta. Okay, so let's just compensate this one. So we have here I max square root of delta. Here we have it as T1 over T. So it's T1 over T, and we have 2 as before. And just after taking the numbers, we have here 100 micro divided by 2 times T is 1 over 250. And after calculating this, you will get 50.31 ampere. But this one is the IRMS one. Let's go for the second IRMS. And that again, from the slides, I peak square root of delta. Delta means the on time. It doesn't need to be the first on time, but any on time is the duration of the on time, okay? And that's again, so I peak equals 150 square root of the T on. The T on is the time. Let's look at that again. The T on is the time between T3 and T2, okay? So we can just say delta is the T3 minus T2, and that all divided by the whole T, because the T on divided by the whole T. Okay, compensate that by numbers divided by 1 over 250. This is the T, 29.05 ampere. So finally now the IRMS of the total equals square root of 50.31 square plus 2905 square, and that will equal 58.09 ampere, and this is the RMS value. So we use the equation of separating RMS to two values and then combining them by the square root of square of them. Okay, and that's it for problem 3.